This is Richard Walker from Elucidate. Welcome to the 8th in this series of videos on AI for computer vision. In the last video, we introduced convolutional neural networks. The introduction of this approach allowed us to deploy a novel architecture. We can divide our AI into two sections. First, a CNN feature extractor. This pulls out edges, lines, corners, and patterns from our images. Second, an MLP classifier. This takes in the outputs of the feature extractor, feeding the classifier with features rather than raw pixel data, improves accuracy. One of the criticisms of AI is that it is a black box. For sure, one can achieve impressive results with these techniques, but it can be hard to explain why. In conventional systems, you can explain to compliance officers and regulators what a system does and how it does it. Using logic in code makes systems transparent. But if your system comprises tens of millions of weights and biases, if your system uses calculus rather than logic, it is much more difficult to explain how it achieves its objectives. Getting regulators and compliance officers to sign off on something that is difficult to explain is challenging. In this video, we're going to focus on tools and techniques that make it easier to explain what the feature extractor and classifier are doing. I hope that the motivation is clear here. A major hurdle for adoption of AI is the inability to describe how a system works. There's a compelling secondary benefit too. The more you can understand how an AI system functions, the easier it becomes to tune it to gain further improvements in accuracy. In this video, we're going to look at both the primary benefit, that is making AI transparent to regulators and compliance officers, as well as gaining deeper insights to help improve accuracy. In the last video, we looked at the convolution operation, the application of small filters to an image to enhance edges and features. Pixel intensities are multiplied by filter weights. We then take an average of the resulting product and transfer that result to an output image. You may recall I said that back in the 1990s, we used to generate the weights in these filters ourselves. We'd use these hard-coded filters to look for specific orientations of edges and then use some logic to apply to these images to create patterns. This is a terrible idea. If instead you let stochastic gradient descent and the backpropagation algorithm do their stuff, then the neural network will pick out the optimum weights in the filters based on the training data that you provide. Now, that's not to say that the network won't figure out line orientation filters for itself. As we will see, it will do that, but it will also pick out much more subtle line and texture filters. These optimized filters will help it extract pertinent features. These features can better differentiate and classify images. Here, we've built a GUI to display the convolutional filters per layer of our network. The grayscale indicates the value in the filter. Black shows large negative values and white shows large positive values. Neutral grey are values close to zero. Among many filters tuned to pull out features in the image, we see some familiar patterns. Here, for instance, in the first layer of the CNN is a diagonal line filter. It will have maximum activation at an edge that runs from the lower left to the upper right. The activations in our output layer will determine our classifications. For a single network, we'll classify an object by taking the output neuron with the highest activation. For an ensemble of neural networks, we'll perform some aggregation on the output layers. For visualization purposes, we can also use the activations of the hidden layers. If we take a fully trained network and feed a sample image into it, then we can see which neurons become active. Instead of looking at the weights of the filters, we're now looking at the output of the filters once they've been applied to a sample image. Our first convolutional layer will pull out edges in the image. The filters will highlight local changes in pixel intensity. The effect of pooling and running a second convolutional filter in our second layer will link these edges into lines. Further downsampling and convolutions in our third layer will result in neurons that are active when lines occur in specific patterns. While our edges and lines are relatively easy to interpret in the first two layers, these third layer feature maps are quite abstract, like monochrome Mondrian artwork. Later in this video, we'll present some tools that help us make more sense of these abstract patterns. Here we can see two images of different bags. Alongside each, we can see the activations of the filters in the first hidden layer. We can see that the filters have picked out strong diagonal lines for the handles of each bag, as well as the horizontal and vertical edges of the bags. The activations here are strong. We're seeing very dark pixels of the bag against a white background. Two filters in the lower left corner of the screen are very active. As we'll see, these are activated by textures in the image. Let's look at a picture of a boot and a coat, which have very textured surfaces. We'll see these two filters in the lower left are both very active. The trousers here are characterized by long, strong vertical edges. We can see this clearly in several of the filters from the first convolutional layer. Let's now look at the second hidden layer and show the images of bags alongside the images of the trousers. Remember here that we've downsampled with a 2x2 max pooling filter and applied another set of convolutional filters. Here, I hope you can see the difference between the images of the bags and the images of the trousers are starting to break down into distinct features. These features can be fed to our classifier. So far, so good. We've seen how easy it is to visualize the filters. We've also seen how we can visualize the output of filters in the first and second layers when we feed an image into a trained network. But there are two nagging problems. Thus far, we've used high contrast images, very dark pixels on a very bright background. What if we show more subtle images? Secondly, we can make out edges and lines in our first two convolutional layers, but deeper into our downscaled third layer, things start to get pretty abstract. On the screen you can see feature maps, characteristic patterns and shapes that define an object's bagness or pulloverness, but these maps are quite hard to interpret. Furthermore, there are such a lot of them that it's very difficult to discern what combination of them make our classifier think that a shirt is a shirt or a bag is a bag. If my job now depended on getting approval for my classification system, I'd fail. Based on this visualization, I would struggle to make it clear how this AI achieves its objectives. Now, for sure, if this is just a simple image classifier, then who cares? But what about convincing a regulator that my AI solution for margin and collateral calculation was fit for purpose? A risk officer that my loan default system could be implemented? A compliance officer that I have a solution for better predicting ratings changes for corporate bonds? No matter how much backtesting data I have or how effective my system proves to be on live data, the chances of putting any AI into production are diminished unless I can give stakeholders a better insight into how the AI works. Fortunately, there's help here in the form of a technique called TSNE. More on that in a few minutes. Let's address the first problem, low contrast images. Here are two pullovers. One is black, one is grey. Unsurprisingly, the black pullover on the white background elicits a stronger response from our first layer. If we look at the second layer, the activations are more even between both images. Part of the problem is simply the dynamic range of the screen and our eyesight. The first convolutional layer does pick up edges in the grey pullover, but they're too subtle for our eyesight to see on these screens. A second pass makes these subtle changes more visible. Indeed, if we look at the second layer for these pullovers and compare it to the second layer for bags, you can hopefully start to see some defining and differentiated characteristics for both. Now, might we use this approach to further improve accuracy? In the last video, I mentioned that it's common to follow a convolutional layer with a pooling filter. A few years ago, Andrew Zisserman and Karen Simony of the Visual Geometry Group at Oxford University challenged that orthodoxy and came up with a simple and novel modification. Run the convolution operation twice and then pool. This spawned a family of networks called VGGNet, named after the Visual Geometry Group. If we follow that approach here, we get a huge pickup in performance. Our previous best ensemble score on our 10 colour images was a creditable 80.93%. By following the VGG architecture, we can improve that to a very impressive 89.51%. The best individual network from that ensemble scores just over 86%. Sure, it classifies a horse as a car, a ship as a dog, and 2 deer as ships, but its performance overall is incredibly impressive. If we apply this to our numbers and clothing data set, the performance boost is equally impressive. We're able to get ensemble scores of over 99.5% for the digits and high 90s% for our fashion images. Following the VGG paradigm allows us to deal with low contrast images as well as improve the performance of our networks as a whole. The second problem we mentioned was being able to visualize what is going on in the deeper layers of our network. There are a lot of feature maps. They're all abstract. What is it that makes an ankle boot, or a cat? We can show edge extraction and line and corner generation at higher levels in our network. We need an effective way of showing how the pattern aggregation works. A strong analogy here is an EEG. Neuroscientists can better understand the human visual system by presenting a volunteer with different images and seeing which biological neurons fire. We can do the same. Indeed, this is what we've been doing with our CNN filters. We show an image to a trained network and then show the edges, lines, and feature maps that light up. In the earlier layers of our network, these neurons form spatial patterns that we can interpret. But deeper into the network, the patterns are less spatial and more abstract. How can we visualize the patterns of activation that indicate that the network has seen a cat or a ship? Well, let's do exactly what the neuroscientists do. We'll train a whole bunch of networks on our colour images as well as our numbers and clothes and keep the ones with the best accuracy scores. Then we'll take a trained network and show it a bunch of images that it has not seen and record its accuracy. But rather than just record the activations in the output layer, we'll record the activations in the deep hidden layers too. Just like the output layer, these activations will be vectors of numbers. We then need a way to cluster these large vectors. Much like the human EEG, there should be clusters of similar activations when our AI is presented with similar images. That will help us determine patterns of activation that enable the network to classify. I mentioned earlier that we're going to use a technique called TSNE for this. TSNE stands for T-distributed stochastic neighbour embedding, not my name. It was proposed by Laurens van der Maten and Geoffrey Hinton in 2008. It's an example of an unsupervised learning technique. By that I mean it uses the similarity between data points for classification. This is unlike neural networks, which work by supervised learning. They use labelled training data and backpropagation to form classifications. TSNE is one of my favourite techniques for data visualization. It works particularly well with neural networks. The next video explains TSNE in much more detail. Here's a quick overview. Once we've trained our network, we can pass through some data. The output of our feature extractor, the CNN bit, will be sent to our classifier, the MLP bit. The input to the classifier is just a vector of floating point numbers. If we send a picture of a cat, we'll get a vector. If we send in another picture of a cat, we'll get another vector. These vectors will not be the same, but if the network is working, they should be more similar than the vector generated when we send in a picture of a ship. The problem though here, and it's a huge problem, is that these vectors are big. Our input layer of our MLP classifiers in this example is made up of 1024 neurons. So we're dealing in a vector space of 1024 dimensions. We're also dealing with more inputs than just two pictures of cats and one of a ship. All of our thousands of images will have their own corresponding 1024 dimension vector input into our classifier. Figuring out how similar two 1024 dimensional vectors are is a lot to wrap your head around, but we can come up with a measure of similarity that's simple to compute. The distance between two n-dimensional points is shown on the screen. The specific case of the distance between two 1024 dimensional vectors is shown right at the bottom. Now, while you wouldn't want to calculate this value by hand or with a calculator, it's a simple routine to implement with a few lines of code. In that way, we can calculate the distance between any pair of vectors that are generated by two images. We can calculate the distance between two vectors that are generated by pictures of cats, which should be close, as well as the distance between vectors created by entirely different classes of image. The clever thing that van der Marten and Hinton proposed in 2008 with TSNE was, we can't perceive things in high dimensions, so let's not try, but we can see things in 2 and 3D really clearly, so let's focus there. We know there's a simple way to calculate the distance between points in very high dimensions, the Euclidean distance. So let's show a plot in 2D or 3D that preserves the distances between the points. That way, we can see points that are clustered together. We'll go into the details on how to implement TSNE in the next video, but what we see here are points that are similar in high dimensional space are clustered together in 2D and 3D. In these lower dimensions, we can see and make sense of the data. This simple intuition allows us to see the combinations of neuron activations that allow the classifier to categorize the images. This is our EEG for our deep layers. These TSNE plots are from one of our networks trained on digits. Each of the dots on these charts represents a single activation vector in a deep hidden layer in our network. TSNE puts points close together when their activation vectors are similar. This results in these clusters. I've then added colour. The colour represents the digit that caused these activations. This clearly shows that the network has similar activations when presented with 7s and characteristic activations when presented with images of 3s, for example. You can also see where the network gets things wrong. There are 4 images of 5s shown here that produce activations more commonly associated with 3s. We'll look at more examples like this in the next video. So a lot to take in. Let's recap and rephrase. We can process an image with a series of filters. These filters are tuned to look for edges and textures. Each filter will produce a strong activation when it encounters a specific type of edge or texture, and low activation otherwise. The output of these activations is then downscaled and sent to another layer of filters. This next layer of filters is tuned to spot aggregations of edges into lines. Again, they will produce very strong outputs when they see lines in specific orientations and low outputs otherwise. Another set of downsampling and filtering will produce strong activations when certain intersections of lines form specific patterns, and weak activations otherwise. These pattern activations will be very similar for similar types of images. Just as importantly, they will be very, very different for different types of image. These activations can be flattened into a vector and then fed into a classifier. What TSNE does is shows us which of these high dimensional vectors are similar. It does this by clustering points on a chart, and the closeness of the points on the chart is a function of how close the corresponding vectors are in their high dimensional space. We've covered much in this video. We've seen how we can visualize CNN filters as well as interpret the output of these filters as feature maps. We've looked at the VGG architecture to help improve the accuracy of our network. Finally, we've introduced a powerful, unsupervised learning technique called TSNE. This helps us better understand and explain the hidden layers of our neural networks. This is Richard Walker at Lucidate. Please join me in the next video where we'll take a look at the wonderful world of TSNE.